From South Bend, Indiana, welcome to 3Degrees Discussions. I'm your host, Mike Vasquez. This is a podcast devoted to the stories behind the innovators, entrepreneurs, and leaders in the 3D printing industry.
When you sign off, there's an expectation that people are not going to get hurt or injured. So our biggest problem with additive has been our failure to understand the complexities of the material. And that is complicated because each build represents a different material system, if you will.
That was Bill Pilgrim Frazier. Dr. Frazier founded Pilgrim Consulting LLC following a successful 39-year-long career with the Department of the Navy. Upon retiring, he held the positions of the Navy's Senior Scientist for Materials Engineering and the Chief Scientist for the Air Vehicle Department at the Naval Air Systems Command, or NAVAIR. Dr. Frazier received his BS, MS, and Ph.D. degrees in Materials Engineering from Drexel University. Before we get started, head over to www.3degreescompany.com and subscribe to the podcast. Remember, you can listen to the show anywhere you download your podcast, including Spotify, Apple, Amazon, or Stitcher. Also, if you or your company are looking for materials, qualification, or general additive manufacturing support, reach out to the team through our website or via email at info@3degreescompany.com. All right, Bill, thank you so much for joining the show today. I'm super excited to hear your story and kind of the work you've done to support and expand the use of additive in the industry. So I like to start these conversations way back at the beginning with everyone. So tell me a little bit about where you were born, kind of where you grew up. Was there any kind of moment or memory in your mind that kind of got you on the path towards engineering and what you've done in your career?
Well, first of all, great to be with you. I'm glad you do this type of thing. And yes, well, I grew up in the Philadelphia area. I was born and raised there. So spent most of, well, I can't say that anymore. I was going to say most of my adult life, but it's been a while since I've been down here in Southern Maryland. I grew up initially in a middle-class family, and my mom and dad separated. So, and in that time, it was, I would say, we were impoverished. We didn't have much money.
Mm-hmm.
So, but my dad gave me a sense of science and engineering. It's amazing how things have changed. He taught college, but never had a college degree. And that was something I don't think you would ever hear about today.
What did he teach?
Business and business writing and marketing. So he taught at Temple and university and so forth. I'm going to pause for a second, Mike, because my daughter walked in. I want to let her know.
Sure.
Okay, I'm back.
Perfect.
Yeah. So, yeah, I think he gave me a sense of science, engineering, and he gave me a sense of curiosity. And that led me on. So I don't know how much of my life history you want to hear, but as I said, I grew up poor. I went to high school in Northeast Philadelphia, and I got put in with a group of brain whizzes that I don't know how I got in there, but I was able to be. They had a program for space and aeronautics at the high school. So that was exciting. And then when I graduated, go ahead.
Yeah, did you like school? Was that kind of a passion of yours, or like were you kind of hit that curiosity itch, or
I didn't until about middle school,
okay.
and after I, I was bored basically with a lot of the stuff and did pro forma things.
Yeah.
Went through the motions. But when I was introduced to challenging concepts, that's when I started uh, getting more excited about it.
Did you have a favorite
So
subject or favorite class?
I liked math and physics.
Okay.
Chemistry was good also, but
Yeah.
and so the typical geek subjects. I liked them because they challenged me. Not uh, it wasn't a facile thing. I I won't say they were easy, but I I excelled in them. And when I graduated high school, as I mentioned, that financially I was pretty poor, so I qualified for what they called a Temple Opportunities Program, full paid scholarship to Temple University. Um, and I chose a pre-med curriculum. And I went for a few weeks, and then I decided this wasn't for me. I wanted to find myself. So I found myself at a McDonald's working as a trainee manager. Found myself in a three-color printing outfit, scrubbing rollers and rifling papers. And then I found myself working for a land surveyor as a chainman, rear chainman. And I spent 2 to 3 years doing that. And that sort of, again, spurred my interest in engineering. And I took some courses at night. I also got a correspondence degree in land surveying. So that was fun. But at one point, I was laid off, and I decided this would be a good opportunity to go back to school.
Yeah.
And I still didn't have a lot of money, but so I went to Philadelphia Community College for a year and a half, and then I transferred to Drexel University, where I ended up getting my materials engineering degree and a position with Naval Air Development Center.
And so with that, I mean, like it sounds like you were hustling, right? Like, I mean, you're like,
Yeah.
you're not standing still when you say you find yourself, when some people say you find yourself, I'm going to go on a long hike in the woods, right? But like you were doing all sorts of different things and kind of came back to school. So what about materials engineering kind of drew you in that direction? Was it back to that kind of like in high school where like math, physics, chemistry kind of mix? Was there anything else?
It's I would love to say it was well thought out and altruistic, but I had three friends while in community college. We were all taking engineering, and we took a visit to Drexel, and we had the landscape at the time was that chemical engineers were making the biggest money. So we wanted to, and electrical engineers were absolutely at the top. So we went to the electrical engineering department, and they told us, yeah, but we weed out about 50% in the first year. And the chemical engineering, it was in the bowels of the building, dirt, grime. It wasn't bad, but mechanical engineering was fascinating, but at the time they were fairly low paying. And same way with civil engineering, only they were even a step below mechanical engineering at the time for pay. Then we visited this little department called materials engineering, and they showed us TEM and an SEM and X-ray diffraction and differential scanning calorimetry and air-conditioned rooms and, you know, like lots of gee whiz type of stuff that was attractive. So two of us ended up taking materials engineering courses.
And how did you what was the path then to the Navy, to the naval side of things?
That's another fascinating story, at least to me.
I feel like I could ask about 20 questions on each of these things. So since we only have 40, I'm trying to we'll hit the highlights, but we'll have to do a longer form 5-hour conversation next time we're in.
Yeah, don't want to bore your audience, but yeah, I had a couple of Drexel is a university that has co-ops, so I had applied to the Naval Air Development Center as a co-op, and I didn't hear back from them. So I had two other co-ops. I had one at Haganus Corporation, which is a powder metallurgy company in near Trenton, Camden. And then I had another one in hydrocarbon research, which was in Trenton. And so I was looking. I was a junior, and I went to the senior picnic, and a professor, Mike Kozak, who actually turned out to be my Ph.D. thesis advisor, and a Dr. John DeLucia, who was the head of the materials department at Naval Air Development Center, Warminster. Mike introduced me to John, and he gave me a good introduction. And John said to me, "Why haven't you applied to the Naval Air Development Center for a co-op?" And I said, "I did." And he did a little cuss, and he said, "Damn it, let me check into this." And they went back, and somehow my application had got lost, misplaced, or whatever, and so I was hired as a co-op, and that's the long story to get to your what should have been a simple answer, but that's how it happened.
Can you talk about, so for people who aren't familiar with kind of the is short for NAVAIR, is that another kind of, or is it different? So Naval Air Development Center, are those two one and the same, or not so much?
Different.
Okay.
What you have is Naval Air Systems Command, which is the top level Navy aviation. And under that, there are warfare centers, Naval Air Warfare Center, Aircraft Division, and Weapons Division. But at the time that I was there, they didn't have those warfare centers. They were called development centers.
Got it.
So the Naval Air Development Center was it became part of the Naval Air Warfare Center.
Okay.
And just a side note, we had a centrifuge there in Pennsylvania Bedrock, in which the original astronauts trained. So years before, but go ahead. I'm sorry.
And what's the mission of Naval Air Development Center, or and kind of what were you coming into as a co-op, and then later on, and what's the broad strokes of what do they do, and then what were you gonna do for them at the time?
Well, yeah, we're talking it's kind of ancient history, but it's in the 1979 timeframe. So organic matrix composites were just evolving at that point. And so I was put into a team of composites folks, and were developing processes for what turns out to be the F-18's wing structure. And repair techniques and so forth. So my co-op experience was started there at that point. But the overall mission was to provide the research and development needs to make the Navy a smart buyer.
Got it.
And so we educate our people who are then in the acquisition that buy these multi-million-dollar weapon systems.
And so a lot of it is like you're doing research on new materials, or people are doing, like, generally, like yourself included, new materials, new processes, repair, qualifying, all of that, kind of around a broad range of materials or systems.
Yeah, well, it's always focused research.
Okay.
For the development centers. It's what's known in the budgetary language as 6.2 or 6.3 type work. So applied research that will transition. So it's at a TR level, technology readiness level of perhaps 3. You're trying to mature it to 6, so it can be adopted by the program offices.
Got it.
Because they basically won't touch anything that's at a technology readiness level lower than 6.
And so you're doing your co-op. You got a co-op at the Naval Air Development Center. You also kind of hinted at the Ph.D. What was that kind of transition, or like what were you doing, and were you working at both places? What spurred on the Ph.D.?
I did both my master's and Ph.D. while working full time.
Okay.
So I spent 8 hours at the Warminster, which is where the Naval Air Development Center was. Then I drove an hour south to Drexel, and they had classes 6 to 9 in the evening. So for the master's, I did that 2 to 3 days a week to get, and then for a PhD, I was I guess in a unique position because the Navy funded my PhD work, and so I wasn't dependent on a prof trying to get money from an AFRL or an ONR or NSF. So that was good and interesting. Couple of things though, my master's, I was going to have a master's thesis, but when I went to publish it, I was informed by Navy powers to be that it was ITAR restricted and I couldn't publish it. So I had to hustle to do some other type of coursework to get by with that. And so that was a scary moment. But it taught me a lesson. And then when I went for my PhD, I convened a meeting between the Navy and the university and had them agree that if I did research in this area, that it would be publishable.
That's important.
Yeah. And that worked out well. But
that's great.
So.
And when is the first time that additive manufacturing came into your vocabulary, or when did you see it? Once?
Long time later.
Okay.
It's interesting though. additive manufacturing's been around for decades, but as a structural material, it has not. So prototyping was done even back when I was just fresh out of school. Um, LOM, laminated object, something or other modeling. But it was essentially fiberglass sheets that they would place down and make a 3D object.
Mm-hmm.
And when you think about composites, composites are additive in a sense that they're filament winding and things like that. But they weren't called that. So it was when I was, well, not to skip an important point, in 1995, they closed down the Naval Air Development Center in Warminster as part of the Base Realignment and Closures Commission. So they consolidated Navy bases to Pax River, Patuxent River, Maryland. That was a big transition. We lost, I would say, about 65% of the people.
Wow.
And I was the designated move group leader, so I had a responsibility to manage all the equipment move and the people move. And when we got there, didn't have any supervisors. so they came to me and said, what do we do? Where do we put these people? And I said, I'm not responsible for these time cards, the whole logistics nightmare. So the commander and the senior executive service at the time asked me to fill in, and I did. But to get to your question, when did additive manufacturing come to vogue? I think I was, well, I know I was the national competency lead for metals, ceramics, and non-destructive inspection. And the Navy had a serious sustainment problem. It still does. Our aircraft and weapon systems are like 30 years old, and they're not designed to be operated that long. So parts fail that were never expected to fail because they weren't to be used. So these weapon systems undergo what they call SLEP and SLAP, Service Life Assessment Program and Service Life Extension Programs. But still, parts were like a forging would be unavailable. Last time it was built was 20 years ago. Where are the dies? Who was the expert that did it? Is the forging machine still there? How do you qualify, certify it? What's the lead time on that? So you would have a part that fails, and you would have a 2 to 3 year lead time to get it up in production. I saw an opportunity to use additive manufacturing to address that lead time, because we could build a part within a week, the same type of part with additive. But the Achilles heel has been the qualification certification aspect of it. So that started me on the journey. It was actually trying to address a continuing problem that the Navy has. Also, the other problem to be addressed with the additive was the Navy's forward deployed. We're on ships. We have stations across the globe. If a part goes bad out there, you have a couple choices. And one choice is to forward deploy enough parts so that they can be there. But that means you have to have supply networks out there and warehouses. Or you can FedEx out parts, and you can't always do that. So the concept of parts on demand, where and when you need them, by ship electrons, not parts, was the concept. Can we build parts nearer to where they're going to be used and then use them? It still hasn't been fully realized even today, but that was the concept. And so we started thinking about that, and I had a workshop early on, and I think 2011, to better understand that. Then I ran a crowdsourcing activity for the Navy to see what additive could do for to address various problems. That was called a Mowgli, massively online war game leveraging the internet. I didn't come up with the name, sorry, but it was extremely successful in gaining attention and so forth. So that's a long-winded answer to your question, I think.
No, that's perfect. And so as a materials engineer, maybe talk a little bit about some of the challenges versus the reality of the qualification part, right? Like, you have the potential, you see you could build a part in metal in a week, but what's in your mind still some of the big barriers that limit those sort of use cases to be, whether it's forward deployed or repair part on demand, whatever it may be?
Yeah, that's a extremely important issue. In my position as national competency leader, I was the certification authority for metals, ceramics, and non-destructive inspection. And so when you're in that position, and there are people in other disciplines that are in that, people's lives are on the line. It's not, when you sign off, there's an expectation that people are not going to get hurt or injured. So our biggest problem with additive has been our ability, our failure to understand the complexities of the material. And that is complicated because each build represents a different material system, if you will. If you build Ti-6-4 in a laser powdered bed system, it's a different material than if you used a wire DED. And its properties are different. And its flaw structures are different. So the questions you have are, what are the properties? Whoops. And are they consistent? And can you control them? So I'm going to digress a bit and get on my soapbox. We need to differentiate between process qualification and parts certification. Process qualification is all about the process and consistently manufacturing a material of known attributes. Whereas parts certification is all about what the part demands of that material. Is it temperature? Is it corrosion? Is it fatigue? Is it static? And the trouble with additive, the challenge with additive, is that you're building both the part and the material at the same time. And so, unlike traditional qualification where you have MMPDS allowables that you rely upon as foundational, you can't necessarily turn to a MMPDS allowables for additive, although they're trying to get there. I've been struggling with it, but the idea is that in the hierarchy of certification, material properties are generally a given, a solid given. You know what they are and you design around them. But with an additive part, they could vary within the part itself. So how do you account for that variation? And also the type of defect structures that you have are not well characterized. So the effects of defects are not known. So you have a potentially net-shaped process that yields a part, but it may not yield the same material. And I'll give you one example early on is 17.4 pH steel, well-known stainless steel, high-strength stainless steel. EOS, a manufacturer, was selling something that looked like 17.4 pH, but it was nitrogen atomized. The nitrogen gas actually was absorbed in the powder and didn't allow for the alloy to age harden to its appropriate strength. So you would have more of a 316L type properties instead of a 17.4. So when we say added materials are not necessarily the same, you have to be really, really cautious. Anyway, I'll stop there.
And maybe let's go back to kind of your own career. So you're doing this work for the Navy. You're kind of leading this investigation into additive, trying to build momentum around, hey, this is a unique technology. We see the potential here. Kind of where did that lead? Like both in terms of your career, did you kind of continue then really focusing on additive, and then what did life look like after the Navy?
Well, and part of my career, I mentioned I was a national competency lead, but then I got promoted into the executive band. It's called an ST. It's equivalent to a senior executive service band or admiral ranked position, only it's technology related. And there were at the time, there were 34 of us in the Navy and 3 of us at the Naval Air Systems Command, an organization of about 40,000. It was at that time I was attempting to get additive manufacturing used because of its possibility of addressing those sustainment issues and other issues. And so moving that forward required recognizing that it was not only a technological challenge that we were dealing with, it's what I call pesty problem, political, economic, social, and technological. So when you're dealing with a culture of engineers and scientists that are comfortable in doing things the way they're done today, and they don't want to change. But an introduction of this new technology required a paradigm shift in our thinking and the way we qualify things and certify them. So it was interesting because I approached many of our team leads, branch leads, division leads, and even at the department level, they all thought I was crazy and that I'm serious. I had people tell me, before an AM part flies, I'll resign. These people are the ones with signature authority. So I went to Tom Rudowski, who was the head of the Air Vehicle Engineering Department. He's now the head of NAVAIR, civilian head of NAVAIR. And he said, Bill, if you give me the data, I'll sign off on it. Because the folks that worked for him said they would never sign a flight clearance. And in particular, we used the V-22 Osprey as a springboard. They stepped up, and we had a Tie 6.4, an engine nacelle link, and attachment point. These are the links that hold the engine on the V-22. So
those are
critical components. Yeah, so they're important. They're not complicated parts, but they're critical. Okay. And we chose that because Tie 6.4 is ubiquitous. We chose it because that in particular, the link we chose had margin, so design margin. And so we went for it with that. And I could spend an hour on this, but we were able to demonstrate in coupon level, part level, and a subcomponent level that the parts were more than met the requirements. Actually, they exceeded the Tie 6.4 forging that was the original part. And just circling back, when it came time to sign that flight clearance, Tom Rudowski didn't have to, because all his division heads were chopping at the bit to have their signature put down, because that was the first safety critical part the Navy flew.
Wow. What year was this, or what was the kind of time?
That was it actually took flight in 2016.
Okay.
And had no incidences whatsoever. So it's still being used as prototypes for other types of experimental work. So.
That's awesome. Yeah, I mean, you must have felt good about that, right? Like that's a big moment.
Yeah. And it was a team effort, because, and I said it was a political, economic, social, technological problem. The one thing that added a div for the Navy is it brought Navy leadership together for the first time that I can remember in my 39 years career at the Navy around a technology. So once it started the ball rolling, there was a one-star executive committee stood up to help guide additive. One star being a rear admiral, lower level, one star on their shoulder. And then quickly went up to a 3-star level that reported to a 4-star at UpNav. And the CNO actually directed that 4-star to hold these things. So we had convened, I would say, every 3 months meetings of this very high-level executive panel to help guide the Navy's approach and Marine Corps' approach to to things. And of course, I'm just a technical geek. I'm not, but it was kind of fun. It was good.
And so, and you've got your own kind of business now, right? That you
Right.
kind of consult with. Do you want to talk about kind of that transition, what you're doing kind of today?
Yeah, sure. I retired in March of 2019 um, after 39 years with the Navy.
Wow.
Got home and I found that I was still anxious to do stuff and add value. So in June of 2019, I decided to open up a consulting outfit, not knowing where it was going, basically. And I chose Pilgrim Consulting as the name because I had used Pilgrim as my avatar in the crowdsourcing. Um, I chose Pilgrim as an avatar because a pilgrim ventures forth into foreign lands on a holy quest. And so I started that, and sure enough, it took off. So I've been, I can't get into all the companies I've helped out, but certainly I've worked with NASA and NIST and indirectly with the Navy. But I like for SBIR supports and things like that. Yeah.
Fantastic. So just two more questions. One is going into, we're at the end of the year here. What are you excited about looking into 2024 and in that quest of continuing with additive and moving it forward?
That's a very good question. Um, I think additives at an inflection point. And when we first started the journey, everyone was tight to the vest with their IP, um, intellectual property. They still are, but not. But as the community has matured, people have realized that in order to sell a product, there needs to be standards built around that product, and so in order to do that, people have to divulge certain aspects, not the secret sauce necessarily, but the certain aspects open up more. So we're at that precipice now, not precipice, inflection point. And a lot of our standards organizations are working feverishly to do that. But the one thing, one of the things that I think has not been satisfactorily dealt with, we're in the era of Industry 4.0, in which we have big data, we have AM, we have collaborative robotics and so forth. But it's the big data. People want data, data, data. But they're not. We're not effectively managing data. As a community, we do a very poor job. So, working with NIST and EWI, we had a FAIR workshop, making data findable, accessible, interoperable, and reusable. It's paramount that we move towards collecting data in that manner, in a structured manner. We didn't have a common data dictionary. The lexicon for additive was poor. So my example is I could say shalom, and what do I mean? Hello, goodbye, or peace be with you. The same thing in additive community, right? Then we don't have a common shared model, data model, which requires a taxonomy as well as an ontology. But you have to have that model, and we need to work together. And so there needs to be a neutral platform or method of exchanging data. So a common data exchange format in which people don't have to reveal everything about their process, but it goes into this exchange and someone else can use it. Okay, so that's going to help lift industry up quite a bit. But we're at the point now that we need to be thinking about another paradigm shift. And that has to do with the way we, our traditional way of qualifying a process. Our traditional means of qualifying a process was we freeze all the key process parameters and they're not allowed to deviate. And so for a rolling mill, that's fine. You know, you roll it at a certain temperature, certain number of reductions and cross, and you get properties, and then you can test it. For additive, it's not so. So how do we, for laser powder bed process, for instance, if we can think of in n-dimensional processing space, a quality processing envelope, if you operate within that processing quality envelope, you could be assured of getting consistent properties. And that requires us to have use a different set of tool set. But what it would do is allow the qualification process to go much more quickly because you qualify that envelope instead of the key parameters. And so that would allow you to be portable from machine to machine because the processing parameters would be able to be portable from machine to machine. It also would allow the qualification authorities to say, if you're operating within that, then you're good to go. As long as you don't deviate outside that multi-dimensional processing box. So to do that effectively and efficiently, we need to blend ICME, integrated computational materials engineering, with the new AI trends, machine learning. Machine learning is effective at sorting things out and identifying sweet areas to for properties, and the physics-based tools would allow us to refine that and to understand it, because things like machine learning, neural networks, deep learning don't necessarily lend to our understanding of the physics. And without an understanding of the physics, put yourself in the person that's signing that clearance. Your machine said it because there is data. Well, what if this happens, that happens? How do you know? So the marriage of those and the use of big data, I think, is important. And then just to tie this up a bit, is we are too stovepiped in our approaches. So the SDOs are working, the standards development organizations are all working diligently, but they're stovepiped. They don't talk as much together. Companies are not talking with each other, but even the institutes aren't. So we need to build a coalition about bringing together these people to have a shared vision on an approach to get us to the end state. And as you know, business interests may conflict, um, politics, economics, all that good stuff comes into play. So it's a challenge, but if we can bring people together to make them understand that it's in their best self-interest to support this activity, I think we'll find a path for it.
Awesome. So last question, kind of a quick, fun one. Throughout your career, any book that really made an impact on you that you'd like to recommend to our listeners?
Oh, there've been so many. You could, well, I would start off with King James version of the Bible, because it sets the foundations for moral and ethics. But there are other books. I was impressed by this very heavy read. What is it called? Ninth Discipline. I think so. Yeah, but it's we deal with so many things in linear terms, and as we all know, things are not always linear. So in terms of environment, right? Say you had an algae in a pond, and it was able to grow, double its size once a day. And you see it, and it's a couple inches, 2 inches. No big deal. 4 inches. Oh, that's not real. 8, 16. It's still not a big. But all of a sudden, you're to a quarter of the size of the pond, and then it's half, and then the next day it's the full pond. And I find that we need to recognize that type of reality in the natural world, or we're trouble. But what other book? I mean, I'm not sure what to say, because I have so many.
That's perfect. I think we'll get started with those two. So perfect. Well, thank you so much, Bill, for joining today. I look forward to seeing you in the new year. I'm sure at many of the AM conferences and talking about AM data and data management. So thank you again for joining and sharing your story.
Okay, thank you. It was a pleasure. It's fun.